So this is page 307, question 3b, and I suggested that and it was one where it said use a suitable substitution, and I suggested that the substitution was either to replace 1 plus x with u, or to replace 1 plus x with u squared, which meant that this was the square root of u squared, so you actually got u. So I said, you know, sometimes it's obvious. I thought in maybe 3a it was obvious what you did your substitution for. Sometimes it isn't obvious, so I tried it both ways. And actually in this case I got the same answer both ways. So here's my little sort of scratch pad, my little rough notes area where I've written my substitution, and I've done the two things I needed to do in this case: differentiate it to get a relationship between dx and du, which was nice and easy, and also to get an expression for x, because the top of the fraction is x. So using that gave me this. Dx just gets swapped directly for du. The square root of u is u to the half. And then I've got two things divided by one thing, which I can split into two separate fractions. So I did that. And I did this step in my head. U to the power of 1 divided by u to the power of a half is u to the power of a half, minus 1 over u to the power of a half, which is u to the power of minus a half. And then I increased the power by 1, so u to the power of 3 over 2, and then divided by the new power, which was 3 over 2, but the 2 popped to the top, so that gave me that. And then increased the power by 1, so minus a half becomes a half, divided by the new power, so the 2 popped to the top, so that gave me that. And then I just did the return substitution at the end, which gave me this. That's not a minus 3, that's just a mark on the paper. So that worked. So, you know, if it works one way, that's brilliant. I then did it the other way, where I replaced 1 plus x with u squared. So that was a bit fiddlier, wasn't it? Because I had to differentiate this implicitly. Well, I could have rewritten it like that and differentiated that, which you can do actually. You can differentiate as a bracket, but this is probably a little bit easier than that. So this becomes 2u du by dx. That just becomes 1. So that's my replacement for dx. I can rewrite it to say x equals. And also I found later on, towards the end, I needed to rewrite it to say u equals. So there were 3 things I did on my little rough notes there. So I replaced dx with 2u du. This is u squared minus 1, and the square root of u squared is just u. 2 things over 1 thing again, but actually, remember this is pulled into the expression, so I was able to cancel out those u's. So actually, I just had this times 2, which gave me that. I could have put the 2 outside, chose not to. Integrate this, increase by power, divide by the new power, integrate that. And at this point it looks like you're going to get a different answer, but of course u is different now. So if u squared is that, then u is that, 1 plus x to the power of a half. So if I do 1 plus x to the power of a half cubed, I get that, and I get that, which was the same as the answer I had got previously. So, so that was good. It worked both ways. It was a lot easier this way. But those questions where it says use a suitable substitution, you've sometimes got to be prepared to have a couple of goes at it. Right, so what I want to do today is introduce limits. So integrating between 2 values, because one of the main applications of integrating is to find areas. And we're going to today talk a little bit about areas towards the end of the lesson. So if I just get my copy open. So we're still on that page 306, 307 double page spread, and it's question 2 on page 306 that we're going to look at firstly. Just get my copy open. So here we are asked to do an integration by substitution, but this time we've got limits, we've got values. So we know that our answer isn't going to be something plus c. When we get that answer, we're going to substitute two values in. And the good news is that actually this is easier because you don't need to do the thing at the end where you replace u with x again. Let me explain why. So I'm going to do part A with you. So this is what we are trying to integrate, and they are suggesting, unsurprisingly, that we use that as our substitution, and that's nice and easy because du by dx is just 1, so I know I can replace du with x, and if I rearrange this I get that u minus 4 is equal to x. So dx gets replaced by du. Always do that bit first in case that allows you to cancel everything else out. X is u minus 4, and then it's multiplied by the square root of u. But what I can also do at this point is I can change these x values into u values. So I move everything into the world of u, and that means at the end I don't need to go back into the world of x. I can do the substitution using u values. So x is 0. Let's remember these are x values. I want to change them into u values, and look, u is equal to x plus 4. So 0 plus 4 and 5 plus 4. So what this now becomes is an integration between 9 and 4. So in a minute, when I've done all my integration, I'm going to substitute in 9 and take away what I get when it's 4. So I'm hoping you can make some progress with that. It's probably easier to rewrite that as u to the power of a half, and remember that that is u to the power of 1. Multiply out the brackets. Yeah. So, yeah. Multiply the brackets. You get two terms that you can integrate separately. Go ahead and do that. And yeah, I'll be sure. Substitute the values. All makes it work. I'm doing a couple of steps in one go here, so the 4's there, coefficients pass through unchanged, u to the power 3 over 2, divided by 3 over 2, 2 pops to the top where it multiplies the 4 to make 8, so that's how that, and similarly I divided by 5 over 2, 2 pops up. Make sure you use your calculator at this point, so 9 arrow x, and then type in 2x to the power 5 over 2 over 5 minus 8x to the power 3 over 2 over 3. get the calculator to do the work, and then go up and change the 9 into a 4. And it trickles through again.
Still. Okay, I'll move.
So I did 9 arrow x, xe, then typed in the expression, and that gave me that one. Extra careful today after my mistake yesterday. I think I've got that right so far. I should just go up and change the 9 into a 4. So I just do del 4 xe. Yes?
How did you get to something over 5?
So when I increase the power by 1, it became 5 over 2, and then I divide by 5 over 2, and the 2 pops to the top, so that's why I get. So if you increase 1.5 by 1, you get 2.5.
Oh yeah, okay. I think I integrated and then times the u outside of this go.
Right, yeah, so you've got u to the power of 1 times u to the power of 1/2, which is u to the power of 1.5.
Yeah, okay, that's fine.
I think this is a rare occasion where I've got it right, but I apologise that they are vanishingly rare. And so we're going to come to areas probably towards the end of today, but if we get a negative final answer for an area, we ignore the negative, don't we, because it's the size of the area, and that negative implies that what we're actually dealing with is an area underneath the x-axis.
All right then. All right. Okay, thank you.
Now, you do get a rather odd thing happening sometimes, particularly when you use trig, when you get this replacement of x values with u values. And sorry, just to be clear, so we're still in the world of u, but that's the final answer. We don't need to do anything at the end because we've changed our x values into u values. Can we have a look at C? Have a look at C. We're going to do B. You're going to have a go at B in a minute. But
Is this still like the same title?
this is integration by substitution with limits. With limits, yeah. So make a start with C, see how far you can get, and in particular, I'm interested to know what happens to the limits when you go from x values to u values. And don't forget that with any integration or differentiation of trig, you need to be in radians. You need to be in radians. C. We're having a go. Remember to do the dx replacement first, on the off chance that that will allow you to cancel out anything with the original question. So I've replaced dx with du over minus sine x, which meant I could cancel out the sine x in the original expression. I've got to remember that minus there. Dividing by minus 1 just makes everything negative. So what I'm going to do is put that there. Although I mustn't forget that minus sign, like I did with the other group. Mustn't forget that minus sign. But this is where, and that just becomes 3u plus 1 square rooted, which I can integrate as a bracket. It's a linear expression, so I just need to increase the power by 1, divide by the new power, and divide by what you get when you differentiate the bracket, which is 3. But it's what happens here that I find interesting, because you should have found that those values became 1 and 0. Now, when we integrate, we're normally integrating from here to here. Small number, big number, because what we're doing is we're saying, what's the area under a graph from this x value up to this x value? Because we've done this substitution, we've got a bigger number at the bottom. How do we deal with that? Well, we deal with it by doing it in the order that it should be done. Not bigger and smaller, but that number we substitute in first. So it's a bit counterintuitive, but in a minute when you've integrated, you're going to do what you get when u equals 0 first, and then you're going to take away what you get when u equals 1. I've changed my x limits to u limits, and it just so happens that now that's smaller than that. But I still do that number first, take away that number, and that's always the case. So go on, have a go at doing that. Increase the power by 1, divide by the new power, and divide by what you get when you differentiate the brackets. We're integrating, so we're dividing, not multiplying, like we do when we differentiate. And then have a go at B and D. Remember, calculator in radians, and let your calculator do the hard work. Oh, and look, I've done it. don't forget you've got a minus sign outside. What can I explain something?
She's got random negatives popping up.
Are you in? Have you put your minus out? Sorry, have you got a negative answer overall?
Yeah.
Yeah.
It's the same answer, isn't it?
But don't forget, we've got a minus sign out.
Yeah.
So negative, a negative answer will be positive. So yeah, you do get some negatives here. So So you end up with 9 over 2 on the bottom, which I'm going to write as 2 over 9. Of course, your calculator will let you write it as 9 over 2 in the denominator. And so my integration comes out with minus 14 over 9, but I had this minus sign outside, so minus 14 over 9 is 14 over 9, which as I recall is the correct answer. Yes. So just have a go at B, which is a little easier, no trig, and then have a go at D, which is a bit harder with trig. And then question 4 is the sort of progression where you've got to work out your own substitutions. So this is on page 306. And this is on page 307.
So I'm confused how you got the 60 moving
Well, I just cheated. Did you get that?
on. Yeah.
So I made x equal to 1 in my calculator and just typed all that in. So, I'll talk you through it. I've got 3 times 1 plus 1, so that's 4. To power 3 over 2, well that's the square root cubed. So the square root of 4 is 2, cubed is 8. 2 times 8 is 16 over 9. But I actually, to be honest with you, just got the calculator to do it. So I did 1 arrow x, and then I typed in 2 open brackets, 3x plus 1 to the power 3 over 2, all over 9.
I go in there on Saturday morning to get a coffee after
Whilst I don't like to talk about, potentially not getting full marks on a question, there will be marks up for grabs, for example, by replacing dx with something to do with du. So even getting that far, I'm well aware that this substitution is really tricky. So, there's, in some cases, it's about trying to grab as many marks as I can. And even if you have to come up with your own substitution and you come up with a completely bonkers substitution, if you correctly replace dx with du using your substitution, you may find there's credit there. So, never give up. Don't forget to change your x values into u values. I know 2/4 is the same as half. Oh, yes. Yes, so differentiate encapsulating sec is on the page 6.
Thank you. Yeah, I did. I did remember it, yes.
If you're not clear on how to use your calculator for the substitution, did that work in the end, George? Yeah. Please make sure you let me show you how to do that, the substitution thing. There's the answer to B.
So when you type in on here to find the limits,
Yes.
how do you type in sec?
Oh right, yes, good point. So sec is 1 over cos. So you're going to do what are we doing? 1 over the cos of 0 to get the bottom one, and 1 over the cos of pi over 3.
Thank you.
Okay, yeah, that's a really good point. I'm glad Beth asked that. Yes, so to work out the sec, you do 1 over the cos of that angle, don't you? Or do the cos of the angle and flip it. So I'm going to do D in a bit, but by all means jump on to question 4, where you've got to come up with your own substitutions. then I can integrate a linear function to the power of a half as a bracket. I increase the power by 1, divide by the new power, and divide by what I get when I differentiate the brackets, which in this case is just 1, so that's nice and easy. Your limit should be 1 and 2.
How did you get? How do you sec it to get your limits?
So that's sec x is 1 over cos of x. So for this, I did 1 over the cos of 0.
Oh, right, okay.
And for this, I did 1 over the cos of pi over 3.
Okay, thank you.
That's, yeah, it's good. It's a good question. It's good to come across that. I'm going to rewrite my answer as 2 u plus 2 to the 3 over 2 over 3. I'm going to stop the video at that point. That's the answer to that one. I encourage you to try a couple from question 4. Right. Yes, I'm sorry, I'm going to say that again. So we know that to find the area under a curve between two values, we integrate. But before integration was a thing, we broke it up into rectangles. So you'd break it up into rectangles or trapezia, and you'd get an estimate. And of course, the more rectangles you use, the better your estimate. And if we say, okay, let's break this area under this curve up into rectangles, there's a little bit of notation that is used in that. So let's take this rectangle here, all right? The height of that rectangle is the value of y for that x value. So that's the height of the rectangle. It's the y value at a particular value of x. When x equals x1, it's the y value, and that's multiplied by the width, and we tend to call that delta x. Delta is a Greek letter, and it just means a change in x. So that's the area of that rectangle, that multiplied by that. And if we're using f of x notation, then the height of the rectangle, the y value, is actually what you get when you substitute that value of x in. So if we take lots of rectangles, we get lots of y values. So that would be f dash of, sorry, it would be f of x of that value, 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 all of which are multiplied by dx. So we get the sum of all of the rectangles, and we have a notation for the sum. And to get the best estimate possible, we make the width of the rectangles as small as we possibly can. Small rectangles, lots of them, we get a better estimate. So we eventually get to the point where, and it's not very big, is it? That if we want to work out the area under a curve by breaking it into rectangles, say between A and B, we can do it by adding up lots and lots of areas of rectangles and by making d of x almost 0. So what we're saying in that notation there is we're saying let's just use an infinite number of rectangles with a tiny, 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 tiny width. And if we do that, what we'll get is the same answer as we get by integrating. This is what integration as a limit means. This is the sort of thing a question would look like. Well, let me show you what questions look like. It would look like this, and I'm going to write that again over here because it's not very big. Question would say, and well, not a gambling man, but I wouldn't mind betting that we'll get a question like this. It would say calculate, and they've got this notation for a particular function. In this case, it's the limit as delta x tends to 0 between 2 and 5 of the function 3x squared 4 multiplied by delta x. That's what the question would say. And all you'd be expected to say is, well, I could break it up into lots and lots and lots and lots of rectangles, but actually I know that all I need to do, because I live in the post-calculus world, is integrate. And the fact we use dx is because it's sort of it's one of those things that's changed over time. It's a bit like me with my rubbish thetas. People's deltas got so crummy that in the end we just started using dx. So actually, I say dx means it's telling us that x is the variable. It actually comes from this here. So this is what you're going to get a question like on the exam. And all you need to do is to realise that this is the sum you need to do. So when you get a question that says that, you are expected to do that. And if you want proof that that is what that does occur, I can offer you proof. This comes from the 5 hardest questions from the few years that NewSpec has been running, and here we go. So they show you a curve. They say this curve has the equation y equals the square root of x. They give you a great long lot of malarkey saying a point P lies on the curve, blah, blah, blah. The area shaded is this. And you've got to calculate that. Only 28% of people got that correct when it was set in 2019. But actually, it was the easiest question on the whole paper because all you needed to do was to do the integral of x to the half between 4 and 9. That's all you were expected to do. So this is how integration as a limit appears on exams. It's a funny old notation. It's very old-fashioned, but it's an easy question. You ignore all the guff and all the nonsense, and you realise that is just asking you to do that. And we'll do that one at the start of tomorrow's lesson.